Okay, this is going to be, I'm going to split this problem into two parts because I just want to remind you what the second derivative test says. So the second derivative test should not be, it's different than it is in Calc 1, but it is close enough that it should be familiar. You shouldn't have to just, it shouldn't be like a completely different thing that you're learning here. So there's two steps. So step one is to compute the determinant of the Hessian. So remember, the Hessian is just what we call the second derivative. I don't know why a guy named Hess got to call this after himself, but he did. Okay, so we want to compute the determinant of this. If this is less than 0, then there's a saddle point. Then the critical point is a saddle point. So we're computing this at a critical point. So if this determinant is less than 0, then we have a saddle point. Okay, if the determinant, I'll just write this again, case 2 is kind of if the determinant of this matrix is greater than 0, then we can split this now into two cases. If the second x derivative is greater than 0, then we have a local min. And if the second y derivative, y derivative is true. If the second x derivative is less than 0, then we have a local max. Okay, so this part right here, go away. So this part right here, this is exactly the test from Calc 1. Remember, this is the second derivative is greater than 0 or the second derivative is less than 0. Okay, the only reason we need to do this determinant check is because if the determinant is less than 0, then we have a saddle point. If the determinant is greater than 0, then we have either a local min or a local max. And we talked about this in class. It has to do with convexity. If this determinant is less than 0, then it means in some directions the function is increasing, so you have like a local min, and in other directions the function is decreasing, so it's like a local max. So if this determinant is less than 0, then say in one direction you have a local min, but in another direction you have a local max. So this is like a Pringles chip, being in the center of a Pringles chip. If you look in one direction, you're like the biggest point, but if you look in another direction, you're the smallest point. Okay, like if you're in the center of the Pringles chip. On the other hand, if this determinant is greater than 0, this means that in all directions the function is either going up, or in all directions the function is either going down. So if you're in the bottom of a bowl, if you look in any direction, it's going up. If you're standing in the bottom of a bowl, if you look in any direction, you're the smallest point. If you look to the left, the bowl is going up, the sides of the bowl are going up. If you look to the right or any other direction, the sides of the bowl are going up. Similarly, if you think about a turned over bowl, so like an upside down paraboloid, and you're standing on the top of the bowl, then you're the highest point. No matter what direction you look in, the bowl is curving down away from you. And you'll probably find it's funny that I'm using a lot of hand motions right now to describe what a bowl looks like. Of course, none of you see that. So I'm using, if I sound exasperated, that's why. It's because I'm doing these wild gesticulations. Okay, in the next video, we're actually going to apply the second derivative test to solve the problem, but I just wanted to have one video where I went over, where I reviewed what the second derivative test was.